So last time I was basically introducing you to quantitative genetics. What I'd like to do now is talk about subdivided populations. So what happens when we move from a single population into what's called a metapopulation. And a metapopulation is essentially a population of populations. And the important thing about them is that the way we typically model it, of course this isn't the way reality works, but the way we typically model it is that we have random mating within these subpopulations and some sort of limited migration between them. Usually for modeling purposes we assume what's called island model migration, which is basically random movement between populations. Okay, so basically if we're going to model genetic drift, there's two approaches which we'll see. There's F statistics and Markov chains. And let's start with F statistics. This is the star-bellied sneetches, if you remember from Dr. Seuss. At least in the U.S., that was a good children's story. It turns out that they're a very good model system for thinking about assortative mating, and that's really the easy way to start. What we can imagine is that if we have a random mating population with two loci, with two alleles at one locus, they will be in the ratios of p squared, 2pq, and q squared. But that's not how star-bellied sneetches work. Star-bellied sneetches have what's called assortative mating, and that is that the star-bellied versions will only mate with star-bellied sneetches, and the plain sneetches will only mate with plain sneetches. And so what that means is that you never get heterozygotes. And so the population in star-bellied sneetches is going to be P, they have a frequency of a proportion P of them will be big A allele, will be big A homozygotes. Proportion Q will be little a, and there will be no homozygotes. Notice this didn't change gene frequencies. It changed genotype frequencies, because if you work through the frequency of the big A allele in both of these populations is P, and the frequency of the little a allele in both of these populations is Q. Now the thing is that Sylvester McMonkey McBean came along and created a machine which essentially randomized who had stars and who didn't. And so he converted this population from this inbred population into a random, well actually I should say assortatively mating population, into a random mating population. And we could ask what happens in that intermediate step? And how would we actually model that? And it turns out it's not that complicated if we're dealing with one locus. Because all we have to do is mix these and imagine that there is a proportion F which mates assortatively, and they mate purely assortatively, and there's a proportion 1 minus F that mates completely randomly. And then we can just simply mix them. So here we have the frequency of the A, sorry, I didn't have it. Oh yeah, so here we have it. 1 minus F, the frequency of the big A allele is a proportion that are randomly mating, times p squared, plus the proportion that are assortatively mating, times p. And that's the number of big A genotypes. Now, of course, real populations don't go and say, oh, I assortatively mate. Some individuals walk around saying, I assortatively mate. Other individuals say, oh, I mate randomly. But what does happen is that you have all kinds of situations where, for example, with flies, a female, when she first becomes receptive, may be very selective and mate very assortatively. And then, as time goes on, as she gets more and more desperate, as her eggs start to mature and she needs to mate, she becomes less and less selective, and eventually does something approximating random mating, perhaps. So that's the sort of thing. So it's not like, there aren't two populations, but we can think of them as two populations. Now this is assortative mating. And I want to mention one thing that I'm about to say, that in this case what we're doing is the mating is taking place based on whether or not you have the star allele. whether or not you have a particular allele. So individuals are going out and saying, I want to mate with you because you have the right genotype. What I'll talk about next is population structure. And that actually has a couple of important differences. The first is humans, for example, mate assortatively on an enormous number of things. Turns out one of the big ones is the width between your eyes, but also height, education, religion, language. All of these are things we assortatively mate on. And some of these are genetic and some aren't. The thing about assortative mating is that if we assortatively mate, if something assortatively mates on a particular gene, it only affects that gene. So if they're assortatively mating for a particular trait, it will only affect the traits which are actually, the genes which actually affect that trait. And maybe a few around there because of linkage. And the important example of this is that, as I say, humans assortatively mate on almost everything. And yet, if we look at something like blood type, that's something we don't assortatively mate on. And within populations, we have within populations, we're essentially in Hardy-Weinberg proportions with respect to the blood type allele, blood type locus. And so what we see then is that, in fact, it doesn't bleed over into all aspects. It's only the genes which were actually affecting the trait which we assortatively mate on. Okay, so this is F, and this is my way of introducing F. And what I'd like to do is define F, and it turns out that the formal definition of F is the correlation between gametes combining to form an individual. Now, in the case I just showed you with assortative mating, why are they correlated? They're correlated because I have two big A alleles, and I'm going out and looking for somebody else who has big A alleles. So they're correlated because you're actually matching genotypes. But we'll talk about population structure. And in that case, individuals will tend to mate with each other because they're in the same place. And that will tend to make them relatives. And it turns out that under those circumstances, we can define F as the probability that two alleles that combine to form an individual are identical by descent. And it's actually a rather fun mathematical exercise, but you can show that the probability that the two alleles that combine to form an individual being identical by descent is exactly mathematically equal to the correlation between the gametes. It's, as I say, it can be done. Now, most of the time we'll be talking about random mating. And with random mating, F, as I say, is the probability that two alleles that combine to form an individual are identical by descent. But with random mating, the two alleles combining to form an individual are the same as two alleles in two different individuals. And so it's just, F simply becomes the probability that two alleles in the same gene, in the same subpopulation, are identical by descent. Anyway, the probability of identity by descent is the same for, does not work for assortative mating. So that's something where some issues can come up. Anyway, F ends up being an important thing. This was really a very important distinction that, and Sewell Wright is the first one to figure this out. Prior to Sewell Wright and his F statistics, when people tried to figure out what the genetic variation was in populations, it was an extremely complicated, very difficult process because they were trying to work with identity, what's called identity by state. Two alleles are identical by state if they have the same chemical makeup. So the two big A alleles are the same, are identical by state. Two alleles are identical by descent if they are derived from the same allele in some ancestor. Okay, so in other words, the reason that you look like your brothers and sisters, sort of, is because you share alleles because you got them from the same parent, from your mother and father. And so you look similar because you share alleles that are identical by descent, because they came from the same parents. So, and that leads us to our basic calculation. One of the fundamental calculations we want to do is, how does F, Wright's inbreeding coefficient, how does that increase? And it actually turns out that the way to think about this is just simply to imagine random mating. And since it's random mating, we don't have to go through the two allele, think about diploids. We can just treat the alleles separately. And we can imagine that we have a hat. And in that hat, we're going to put all of our alleles that are in the population. So if we have a population size of 2, there'll be 4 alleles in there. If we have a population of 8, there'll be 16 alleles in there. And what we're going to do is we're going to create the next generation. And we can imagine that if we have our 4 alleles, we have a population size of 2, we have our 4 alleles in there, we'll label them 1, 2, 3, and 4. Now they may be chemically the same, they may be identical by state, but we're going to say that they're different, they're unrelated to each other, and they're not identical by descent, so we give each one a different number. When we set up the next generation, we want to create 2 individuals. That means we need to draw 4 alleles. And so we're going to reach into our hat, we're going to pull out an allele, and we're saying, allele number 3. We write that down, we throw it back in the hat, stir it up, and reach in again. We say, allele number 4. Throw that in, stir it up, and we reach in again and say, allele number 3. Okay, so that's where it is. Now we have, and then maybe we go in and reach allele number 1. And so what we have is 1, 3, 3, 4. We've lost 2 and 3, allele number 2, and allele number 3 has doubled in frequency in this case. And that's what we mean, essentially what we mean by genetic drift going on. How do we model that? Well, what we can do is we can just think of this another way. We can say, let's reach into the population and say, allele number 1. And we can reach in again, we can say, we got another one. What's the probability that it's going to be allele number 1? Well, if n equals 2 and there's 4 alleles in there, what's the probability? Well, it's 1 over 2n, or 1/4. So the probability that they are, that we will get the same allele is going to be 1 over 2n. What's the probability, since we pulled out a 1, wrote it down, threw it back, stirred it around, what's the probability that we'll get an allele other than 1? 2, 3, or 4? Well, it's 1 minus 1 over 2n. So we've divided that into the probability that we get the same allele, the probability that we get different alleles when we reach in with replacement. If we have 2 different alleles, we pulled in a 1 and we pulled out a 3, what's the probability that they're identical by descent? Because they could have been identical by descent at some point in the past. Right? And here's where the definition becomes almost circular. The probability that 2 alleles are identical by descent is F. So if we pull in an allele and we reach in, we pull up a separate allele, and they are not, and we can ask the question, are they nevertheless identical by descent because of some event in the past? And we have a number for that, and that's F. And so that's the recursion equation here. F at time t plus 1, what it will be in the next generation is 1 over 2n, which is the probability that we grab the same allele twice. And 1 minus 1 over 2n, the probability we grab different alleles, times the inbreeding coefficient in the current generation. And so we can see that it just is going to build up from there. And that's really the point we have to think about. I always like to think of, the image I like to think of is a graduate cylinder, maybe a 1 liter graduate cylinder. And what that does is, we can think of that space here as being the variability in the population, sometimes called the heterozygosity. And so that in our completely outbred population, this cylinder is empty. And then what's going to happen is that when we go through empty spaces, heterozygosity, 1 minus F. Then as we go through that, we can iterate that equation. So if we have, so we start out with a population of infinitely large, it's outbred, we have an empty cylinder. We go through a population bottleneck of 2 individuals. And so if we do that calculation, 1 over 2n is 4, so it's 1/4 plus 1 minus 1 over 2n, 3/4, times 0. And so we multiply that out, that's 1/4. And we fill that up. We fill in water up 250 milliliters of water, because that's how much F we have. Now, assuming we don't knock over the graduate cylinder and there's no evaporation occurring, we can leave this for months. So we can go back to a population size of infinity for as long as we want, and it will stay there at a quarter. It will not go down. This is a major problem for conservation biologists, because once it's gone, it's gone. Once you've lost the variation, it ain't coming back. Now that's not quite true, because selection and genetic drift, and mutation can essentially, our selection can keep that down to some extent. But genetic drift, mutation is very much like evaporation. It's a slow process, but if you leave this for long enough, eventually it will dry out, and the inbreeding coefficient will go back down to 0. If we keep it for a while at infinity, it stays as a quarter, and then we go through another population bottleneck. You can do the math. It comes to 0.4375. We're going to simply add some more water to that to bring it up to that level. And again, it's going to be there. And that, I think, is a really important thing to remember about inbreeding coefficients, is that they accumulate and that they don't go down unless there is migration or mutation or something like that to prevent them from, to basically add new variation to the population. Okay, so let's start with co-ancestries. This is where this gets fun. One of the things which we want to do when you're, the inbreeding coefficients, as I just explained it, make a lot of sense when we deal with single loci. But if we're going to move to a system where there's epistasis or dominance and things like that, we actually need to start thinking about the pair of alleles. We have to think about diploid individuals. And it turns out that it works out exactly the same for one locus, but when we go to two locus, it becomes a little bit different. And what we want to do is, we want to look at the co-ancestry of an individual, among two individuals. And so this is a co-ancestry of an individual with themselves. And what we're going to do is we're going to take the alleles in that individual, A1 and A2, just arbitrarily measured, and compare it to A1 and A2. It's as if we took the alleles in that individual, wrote the numbers on marbles, stuck them in a hat and reached in, and we just keep reaching in and grabbing one and then writing down the number, grabbing another one, and we just keep comparing them over and over again. So what this is the average correlation between the two. And if we grab an A1 allele twice, what's the correlation between them? It's 1, right? And if we grab the A1 and the A2 allele, what's the correlation between them? Strangely, I've switched to capital letters. It is F. It is simply the probability that the two alleles are identical by descent, by definition. And so we can simply do that. We do that over and over, millions and millions of times, and take the long-term average, and it's going to be 2 plus 2F divided by 4, because there's 4 cells, or 1 plus F over 2. And then we can do the same thing with two different individuals. We can grab the A1 and the A2 allele from individual 1 and the A3 and the A4 allele. Doesn't really matter if we take different individuals. We never get the same allele. They're always different alleles. And the question is, how related are those two alleles? The probability they're identical by descent is F. And see, you need to remember, what you're doing is, for any given pair of alleles, either they are or they aren't identical by descent. If they are identical by descent, their correlation is 1. If they are not identical by descent, their correlation is 0. And so when we take the average over a huge number of individuals, a proportion F of them will be identical by descent. So this is sort of the long-term average of the whole population. Anyway, so that gives us theta dA equals F. And then there's also another one where we can take two alleles from different Ds. In the absence of migration, we can just assume that that's going to be 0. Because you can imagine if we're going to grab an allele from this subpopulation and an allele from this subpopulation, there's no way that they can be identical by descent unless we actually have migration going on. And we'll just ignore that for right now. Anyway, the beauty of this is that we can actually use those numbers, those co-ancestries, to arbitrarily, easily calculate variances. And the variance within populations turns out to be 2 theta t minus theta d. You do the math, and that's what we get. 1 minus f, which is times the variance within populations. And this is a standard calculation which you're all familiar with. Makes huge intuitive sense that as you decrease the number of alleles in there, the variation goes down, and this gives us the rate at which they go down in a very nice manner. The variance among demes, among subpopulations, is 2 theta d minus theta b. And of course, theta b is 0, theta d is f, and that's where we get the 2f sigma squared. And again, it makes great intuitive sense. When we start out, we're in Hardy-Weinberg equilibrium and we slice this population up. There's no variation among populations. And then as it becomes completely inbred, f eventually goes to 1, then every population is fixed for the big A allele or it is fixed for the little a allele. And the variance among population has gone up, it's maximized, and it's 2 times the variance of the alleles. On the other hand, the variance within population, if everybody is a big A genotype, there's no variation within populations. It makes a lot of sense. The variation within populations goes down, the variance among populations goes up, and the total variance is the sum of these two, which is theta t minus theta b. You can do the math. You can simply isolate that d out, and it's 1 plus f sigma squared. And so that goes up quite a bit. So, this is what happens. The variance within populations goes down, and this is generation. It could be any arbitrary population size, but it goes down in a nice way. We can actually look at the inbreeding coefficient. We get a nice straight line, that there's a linear decline in the variation within populations. The variance among populations increases linearly with inbreeding coefficient, although if we go by generation, it accumulates slowly at a decreasing rate. So plotted against generation, it's going to be a curve. So that is, in a nutshell, what you learn in a standard population genetics course on inbreeding. So let's move on. Now we want to look at a 2-locus system. We have the A locus and the B locus, and we will actually, I put a line here to suggest that, in fact, they're linked, or potentially linked. So the A1, B1 came from the mother, and the A2, B2 came from the father. And so they can recombine, and so you can get A1, A2 gametes, but you might find that these 2 gametes are the common ones, and those 2 are the uncommon ones, or something like that. Nevertheless, when we do the correlation of an individual with itself, we don't need to pay attention to that. And so we can say, what is the 2-locus coancestry? And what you're doing there is you're saying, what is the probability that both alleles are simultaneously identical by descent? So for example, if you grab an A1 and a B1, and you grab an A1 and a B1, the probability they're identical by descent is 1. If you grab an A1, B2 and an A1, B1, well, the A1 allele, sorry, it's 1. I say 2, it's 1. If you grab the A1, B1 and the A1, B2, well, the A1 alleles are identical by descent. And so the only thing you have is a single locus probability at the B locus. And so that's F. And that's the same here because they share the B1 allele. That's the same here because they share the A1, the B2, the B1, the A2, the B2, and the A2. And the diagonal here is 1. These guys are, if we look at, for example, A2, this one right here, A1B1 and A2B2, that's a chance that the A1B1 and the A2B2 are both simultaneously identical by descent. Now this is kind of a funny one because you might think that in a completely randomly mating world, that would just be F squared, right? Because then you could say, what's the probability that the A1 and A2 are the same? And what is the probability that B1 and B2 are the same? Now it actually turns out that that doesn't have to be the case. That if there's linkage or something like that, this number may be different from that. And I'll just note on notation, I put a 4 there because there's 4 alleles in one gene. Okay, and that actually, if you read through my papers, that becomes an important issue because as we go to a metapopulation, you have to be careful of what, you have to be careful of how many alleles in each gene are involved. Anyway, if we do that, there are now, that should be 16, I'm not sure. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This should be a 16 here. And it ends up being 1 plus 2f plus f4 over 4. And you can see it just all adds up to 1. One of the things you be careful of with these things is you make sure that when everything is inbred, that adds up to 1. And indeed it does here. Although obviously it doesn't there. Anyway, it turns out that that's approximately equal to 1 plus f over 2 squared. And so you can see that really, for all this fancy algebra, we could have just taken our single locus 1 and squared it. So that's kind of nice. I don't want to go through all the stuff, but we could, theta d becomes a little bit different because this is the formula for theta d. Notice it structurally looks the same. Again, these are 2 individuals in the same gene. And so we could grab an A1, B1 from this guy and an A3, B3 from this guy and ask whether they're simultaneously identical by descent. And that would be F4. They have to be different. Gamma, these are all 4s because they're all from the same gene. And the gammas here is saying, remember I told you that we had the gamete from the mother and the gamete from the father? This is, if we had A1, B1, A3, B4. So we've got 3 different gametes. This came from the mother, and this came one from the mother, one from the father, and the other individual. That's why we need a gamma. Delta is 1 from the mother, 1 from the father, 1 from the mother, 1 from the father. So delta is 4 different gametes that it's coming from. So we have to keep track of that stuff if we're going to keep track of linkage. And it's approximately equal to f squared, so we don't get too excited. And then BAA equals 0. So I don't expect you to remember this stuff, but what I do expect you to think about is that in fact we can move beyond single loci. That essentially what we're doing is we're, for the single locus, we're saying, are these 2 alleles identical by descent? For the 2 locus system, we're saying, are these 2 allele pairs identical by descent? Are the 2 loci, the alleles at the 2 loci, simultaneously identical by descent? We can do a whole bunch of math with that stuff. And we can again calculate the variance within genes due to the epistatic variance. And it's approximately equal, and it's exactly the same thing. The only difference is that there's a 4 in front of here. Because there's, instead of just being 2 alleles, there's now 4 gamete types, is essentially where that comes from. Other than that, it's exactly the same equation up at that end, and then we just start plugging in these different co-ancestries, and we get something which is basically 1 minus f squared. And The variance between demes is basically 4f squared. So it works very, it ends up being very symmetrical with our single locus model, although the algebra gets a little bit ugly. And if we do that, this is what we get. And this is the variance within demes. This is the variance among demes. And what I want you to point out, what I want to point out is this is the additive model right here, 2 theta t minus theta d. These are the various epistatic terms. A couple of really interesting things here. One is it increases. The variance within populations increases immediately after a population bottleneck. And this is a total variance within demes. Very odd sort of circumstance. The other thing to notice is that this line is free recombination. This line is just theta t squared minus theta d squared. This is the epistat. This is if we just squared the univariate ones. You can see that it's only with very tight linkage that there's any effect at all. Basically, you get very little effect of tight linkage unless the linkage is very small. And here, this is free recombination, and I didn't put other lines in there because 0.25 is right on this as well. This is all from things which are very close together, and we knew that, right? We know that from molecular data. If you're looking for a signature of selection, you know that it doesn't extend very far along the genome. That recombination very quickly randomizes these things. This shows the variance among demes. This is the additive expectation. It goes up by 2. And the epistatic expectation, it goes up 4 times the epistatic variance. So it really, so that's the other thing which epistasis does, is it really changes a lot. You get this increase in genetic variation within demes, and you get this, it magnifies itself. It has twice the effect for a given amount of epistatic variance. It's going to have twice the effect on the variance among demes, as will the additive effect. But that's kind of interesting, because this is the variance within demes. And that's really pretty boring, because we don't know what to do with that. There's lots of things which contribute to variance within demes, and specifically and very importantly with epistasis, that's genetic variance which is by definition not heritable. It cannot contribute to a response to selection, as I showed you last time. And so this is not a very useful term. It doesn't tell us how the population is going to evolve. It does show us that something weird is going on. In fact, I can tell you that when I first tried to publish this, I got one of the reviewers came back and said, "I don't know what you did, but it's wrong." And at that point, I had no idea why this, I didn't have the intuition as to why this was happening. And I wrote back and said, "I don't know what's going on either, but this is what the equations say." Okay. So, now we're interested in the additive genetic variance. That's what we really want to know. We don't want to know the variance within demes. We want to know the additive genetic variance. And the standard way to do that, as I say, there's a number of ways we could do it. What I chose to do was look at a half-sieve design. And what we do is we take a whole bunch of sires. You can tell I wrote this talk quickly because I didn't change that to sire n. And make each sire to multiple dams. And from each dam we can take a set of offspring. And so we can take offspring that share the same sire, but have different dams, and they're half-sieves. And we can compare those to unrelated individuals, ones which share neither sire or dam. And so we have half-sieves and unrelated individuals. And it turns out that the variance among half-sieves, if you look in Falconer, 4 times the variance among half-sieves is the additive genetic variance. And you can see why that is if you read his book. Well, I decided to do exactly the same thing, and I created coancestries which are conceptually the same as what I showed you, except instead of comparing an individual with himself and 2 other individuals, I compared the offspring of an individual of one dam with the offspring of another dam. and divided into one dams which shared a pair of sire and dams which did not share a sire. So I have the 1 and 2 locus co-ancestry for half-sibs and the 1 and 2 locus co-ancestries for unrelated individuals, and the additive genetic variance is this. And you can see it has the same structure. We've got a bigger multiplier here. It's got the same structure, theta t, lambda t minus lambda d, lambda t minus lambda d. We do, however, have to subtract off, and I'm not going to show you what that term is. We have to subtract off something because half-sibs will share a similarity because of epistatic interactions. This is something which people have known about for a long time. If you have a very large population and there's a lot of epistasis and you select on that population, you will get a response to selection that will decay with recombination. It goes away after a few generations. And that's coming from this term right here. Because in fact, half-sibs will share epistatic interactions, which will break up. And so they really shouldn't be included in the additive genetic variance. We can calculate exactly what that is and set it and correct for that. So it's not really a huge problem. Anyway, if we do that, in an additive world, this is what happens. This is the graph I showed you before. What I've done here is I've said, here's a population which is half additive, half epistatic at the start. And this is what would happen if there was only additive variance. This is what happens to the actual population. It increases. Now, the increase isn't as dramatic now because the additive component is decreasing. This is a population size of 2. So the additive component is decreasing by 1/4 in that first generation. And that's pulling everything down. Nevertheless, the total variance increases. But, importantly, the additive genetic variance increases a lot. It becomes substantially greater. And then it starts declining, like this. And we can do the same thing using an inbreeding coefficient, plotted against inbreeding coefficient. Oops, I put the wrong graph there. But it does show you the additive. That's totally the wrong graph. This is cytoplasmic traits. Cytonuclear traits. The additive genetic variance should go straight down, and I'm sorry. The additive genetic variance from the epistasis goes from 0, increases, and goes down again. So it looks similar, reminiscent of that. Okay, so that very quickly, and I hope I haven't gone too, well, I have gone too fast, I know that. But that's really the co-ancestry approach. And this was the first way in which I modeled this. And it was the beauty of it, I should talk a little bit about this, because this modeling system is really interesting. It only looks at the mean. And so as a consequence, it's completely independent of distribution. The results I'm seeing here are contingent only on the fact that you can measure the variances. And so if there's additive genetic variance and epistatic variance, this is the expectation. This is what you expect to happen. And what happens is that if there is only one locus, some populations will have a huge increase in variance, some will have a decrease, all kinds of things can happen. And so the variance around this expectation will be huge. Now Fisher, in his infinitesimal model, assumed that there were infinitely many loci of infinitely small effect. And in that case, there is no variation. And this is the exact expectation. And every population should correspond to that exactly. Now the reality is somewhere in between. So if there's one locus, it varies wildly. If there's infinitely many loci, there's no variation at all. When we actually do QTL studies, depending on your cutoff, we often find that there's something in the order of 10 to maybe 50 QTL that are important for most traits that we're interested in. And so in that case, it's going to be some intermediate value. And we really don't know the answer to that. It's an area that deserves some study. So So there's another approach, and this is an approach which I, in my zeal to be analytically clean, I eschewed. I pretended wasn't the right approach to use. And it was the one that Jim Cheverud used, and I subsequently was won over to the Markov chain approach as being actually extremely valuable. And so this is the other approach which we can use. What the Markov chain is that you have, it's a general principle, idea. You have an array, you have a vector which describes all of your states of whatever it is, all of the possible values of your populations, all the states they can occupy. And then what you do is you have a matrix which is going to give you a transition and is going to convert the vector in its current state into the vector in the next generation. Okay? And this is used in a huge number of, it's used in systematics, and it's used in a lot of different fields. In biology, in genetics, where we can use it is we can say, here's a population of two individuals. So there's 4 alleles in there. And I'm just going to show one locus to give you an idea of it. There are exactly 5 possible states. You could have 4 big A alleles and 0 little a alleles, 3 big A alleles and 1 little a allele, 2 big A and 2 little a alleles, 1 big A, 3 little a's, and 0 big A and 4 little a alleles. And in that case, in this population then, we can see that there is one population that all of the populations, all of the populations start out with 2 big A and 2 little a alleles. We can put any numbers we want to. Clearly this has to add up to 1 because this is a probability distribution. And so you have to be in one of these states. So no matter what, this always adds up to 1. So that's the idea. And, it can be any number of things. Here, as I say, this was one where everybody has 2 big A alleles and 2 little a alleles. Here's where every population type is equally frequent. Here's one where either you're fixed for the big A, a population is either fixed for the big A allele or fixed for the little a allele. So all of those are the same. Notice they add up to 1 in every case. And, so all of those are valid vectors. I would also point out that notice this one, you could have you could have a homozygate big A, and a homozygate little a. You could have 2 heterozygotes. We are not distinguishing between those in this case. Again, that's the assumption of random mating within those populations. Okay. So, what we're going to do is create a transition matrix, and basically the heart of the Markov chain is a transition matrix. The transition matrix uses linear algebra to convert a population vector of one generation into the population vector of the next generation. Remember, it's describing all possible states. And so what we're doing is, here's our transition matrix. This is our population vector. This is a population vector in the next generation. And we can do this. And it's really, it's very satisfying. If you know your linear algebra, you can actually solve this the matrix and figure out what the stable structure of this vector will be, and you can calculate all kinds of interesting things off of it. We're going to blow that idea out of the water. Anyway, what is the transition matrix? The transition matrix is the number of alleles. What it does is it tells you what the population in generation T will be in generation T plus 1. So if you have a population with 2 alleles, 2 big A alleles, then, so you have any given population that has 2 big A alleles, the next generation, 0.375 of the population will have 2, 25% will have 1, and 6% will have 0. 25% will have 3, and 6% will have 4. And so what you can see is that what this is doing is it's just using, if you're familiar with probability theory, this is just the binomial distribution there. And so it just gives you the elements, the probability that given that you're sampling with replacement for 2, that you will get all these different states. A couple of things to notice here. You know, if we start out with 1, yeah, you can end up with 4 big A alleles, but the probability is less than 1%. Whereas you have a much higher probability of going to losing the big A allele. You tend to lose the rare alleles, but it doesn't have to happen. The other thing is that if you are in an absorbing boundary and there's no mutation, if you are fixed for the big A allele and you sample with replacement, fixed for the big A allele and you sample with replacement, you're still going to be fixed for the big A allele. So fixation is an absorbing boundary, and you'll find that those occur throughout. So, you know, if we want to do it, you know, this just writes out what the TIJs are for anybody who doesn't know their probability theory. I leave it to you to ponder it at your leisure. Okay. Okay, all of the rows have to add up to 1. After all, you have to be one of those states in the next generation. 0 and 4 absorbing boundaries. Once a population is fixed, for big A or little a, it stays there. Those are the absorbing boundaries. And every population will eventually fix for one or the other of them. Again, the way we typically model this, if you think about this as it's a random walk. You're starting at some place, you know, we start you at a tree, and we give you a whole bunch of beer to drink, get you really drunk, blindfold you, spin you around, and send you stumbling off. Where will you go? Eventually, you'll run into a ditch and you'll be stuck there, because that's an absorbing boundary. And so we'll all end up in the ditch. Okay, and so we can calculate this stuff, and I just, again, I leave you to ponder this the next generation, for the next generation, and yeah. Okay, but if you were to calculate this, this is what you would find out. The population, this population started this is for an n equals 16, so there's 32 alleles, right? And so they started out the population with 16 big A alleles and 16 little a alleles. And that's not shown here. That's that first one, which was the generation before. And then what's happened is that just by random sampling, we've gotten a population which has started out like this. Eventually it rounds out, and eventually it becomes essentially a flat line which goes down slowly. And what happens then is that these two absorbing boundaries start absorbing things, and eventually everything will be in this category or that category. That will take a long time. Now, here's the important thing to notice about this. Yeah, if we take the average of all of these populations at any different time, and we were to calculate the inbreeding coefficient F based on those co-ancestries that I told you about earlier, we would get exactly the same variance within populations. But the F statistic would give us the mean variance, which is averaging over all these. Notice that many of the populations have 0 variation, and there's some populations that have absolutely as much variation as they had in the beginning. So all of those things can occur, and what the F statistics are giving us the average. This is actually giving us the entire distribution. And so the beauty of the F statistics is we don't need to know anything about the number of loci, or the number of alleles for that matter. We don't care. All those things do not affect the mean. But it tells us nothing about the distribution. So when we actually do an experiment, and we don't know how much replication we need for that, doesn't give us insights as to how much replication we need. Essentially those inbreeding, the co-ancestries tell us that the additive genetic variance should increase. But in any given experiment, any given lineage, it may or may not increase. And we don't know the answer to that. And so that's really a problem. It's kind of remarkable because one of the things that happened right around the time I published my original work on this is that there was a group in Texas, Meffert and the name's escaping me at the moment. Anyway, they showed that there was an increase in inheritability following a population bottleneck. And when we look back at that, they were very lucky. In other words, they really didn't have enough replication to be able to say that, but they got lucky, and that's the sort of thing we don't really know the answer, how to deal with that. This, on the other hand, gives us a distribution. We can calculate that mean. It turns out the mean is the same. We can also see the distribution of possible population types. And we can ask, what is the variance in the variance within populations? What is the variance in the sample variance? The problem with that is that we are specifying the number of loci and the number of alleles. And that's fine if we know what those are. But in the real world, we often won't know. And so, which is better? I can't really say. It depends on what information you have. This does have one huge advantage, and that is we can switch over to a two-locus Markov chain, and it becomes much easier to model different types of genetic interactions. The easy way is to assume that populations are always in two-locus equilibrium. And if we assume that they're in two-locus equilibrium, that they are freely recombining and that they're always mixed together, then the two-locus Markov transition matrix is just simply the product of those individual matrices. It doubles, it squares the size of the matrix. And in fact, probably the right way to think of it is to think of it as a tensor. Tensor is a matrix in multiple dimensions. So basically, it becomes a four-dimensional tensor. Or a computer geek would say a four-dimensional array. That's, if you're programming it, you have four subscripts on your array. Now, later on, I will show you the hard way. And the hard way is to keep track of linkage disequilibrium. And then it's not just simply squaring it, because, of course, you have to keep track of how different the different populations will be in terms of the frequency of the different types of gametes. And so it turns out you have to keep track of three parameters. A1, B1, the A1 allele, the B1 allele, and of course, once you've kept track of the A1 allele, you know the frequency of the A2 allele, because that's simply 1 minus A1. And the B1 allele, so now we know the B2 allele. We also need the A1, B1 gamete. Turns out if we know that one, we can know the other three, because that gives us a handle on the linkage disequilibrium. The problem is that this tensor becomes very large, very fast, and the transition matrix is a six-dimensional array. So it gets huge. Anyway, but the beauty of the Markov chain approach is that any two-locus interaction is very easily modeled. For example, it turns out that there are 9 different cells here, right? And so if there are 9 different cells, then we can extract the mean, and that leaves us what are called that leaves us with 8 degrees of freedom. And that means that there are 8 orthogonal, independent ways that we can put interactions together. And this has been my approach. Jim will give us a somewhat different approach in which is based on a different motive. But it turns out that once you have these 9 cells, you can fill them in any way you want. And this is the way I've chosen, and I think you can appreciate the logic. The A locus, I call it the additive A locus. What we're doing is we're simply ignoring the B locus at this point. And so we have additivity with A1 being large and A2 being the small. And then we can do the same with the B locus. Again, B1 to B is large, B2. I still didn't fix any of these up. But I'm so sorry. They're supposed to be B1, 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 B2, and B2, B2. You can't proofread on small screens in airplanes, apparently. Here's dominance A, And notice this is really interesting because when you think about dominance, most of us think about directional dominance, right? We think about, you know, little a being 0, heterozygote being 1, and the homozygote being 1. But that is, if we think about it linearly, that's like this. And what I think of as dominance is that, overdominance. And so the directional dominance we're familiar with is actually a mixture of dominance and additive. And so pure dominance is just simply overdominance or underdominance. And now, while I've done these, you know, as -1, 1, and -1, equally valid would have been 1, -1, and 1. You know, you could do it either way. And effectively, they will do this. They will have the same effect. Again, dominance B locus, the additive by additive, 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 additive. The dominance by additive, the A locus is overdominant, 0, or underdominant. The B locus is additive with the direction depending on the A locus. And additive by dominance is the reciprocal, and then finally dominance by dominance. These turn out to be orthogonal to each other, independent. And from your statistics class, you might remember how to figure that out. But in fact, they are completely independent of each other. And that's why I like them. Gyms are not independent of themselves, of each other, but they fit more logically into the quantitative genetics that I introduced to you last time. And that will forever be an argument between the two of us. Not a very strong one. Anyway, if we do that, this is a, you know, here's the additive genetic variance, and this is the additive expectation, which, as I say, declines linearly with inbreeding coefficient. But here we have all of the other systems. Here's just the different dominance, A or B locus. This is the additive by additive epistasis, which does the biggest conversion. And the biggest conversion takes place right about inbreeding coefficient of 0.5. Dominance by dominance, and additive by dominance. So we can just plot these things right here. And it works really nice. And all of these, of course, remember they're orthogonal. They're independent of the additive component. So the inbreeding coefficient of 0 in a completely outbred population, none of these, except for additivity, contribute to the additive genetic variance. What happens is they no longer become independent as inbreeding proceeds. And so what happens is that's why you get that conversion taking place. Okay, so this is kind of an interesting question. Before I showed you the variance, I showed you the additive genetic variance for a population, right? And I showed you how I calculated that using these lambdas. And so that, if you look at that equation at the top, that is the additive genetic variance in populations. Well, once we've done that, we can do, when I talked about the variance among populations, I can do the same mechanical operation, putting D's and B's here, as I did for the variance within and among populations. And now we have to ask, what does that mean? What does that term mean? And that's sort of a mathematical way of saying, what the heck did I just do? And that's something that mathematicians will do once in a while. They say, hey, let's do this. What does that mean? Well, actually, it has a very fundamental question. And that is, I see an increase in the additive genetic variance here, right? And I can show it for almost any of these I can show it for all of these epistatic interactions. Where is that coming from? Because I told you what additive genetic variance is. It's the variance in breeding values. There's no magic there. And so if you're decreasing the variation, how can the additive genetic variance go up? It turns out that there are only two ways to increase the additive genetic variance. One is to increase the number of alleles, make more alleles which are more different. And we know that genetic drift can't add alleles. It's decreasing the number of alleles. That's just the way it is. The other way we can do it is we can spread the alleles we have apart. So that's exactly what's happening here. That is what, we must be spreading those alleles. So we're starting out, if we can imagine that this is the array, the range of breeding values, and we can mark particular individuals' breeding values, when we go through that population bottleneck, or maybe these are average effects of different alleles, when we go through that bottleneck, those average effects must be spreading apart. We have to ask, how is that spreading occurring? And again, you can imagine, what I like to think about is that there's two ways that spreading could occur. One is you could just have a change in scale. I think it is very much if you go to the park and you buy a balloon with Mickey Mouse on it, and you blow that balloon up, before you blew it up, you had a little Mickey Mouse. After you blow it up, you've got a big Mickey Mouse. And that's just a change in scale. You're just spreading the points farther apart. But what would happen if you bought a balloon with Mickey Mouse on it and you blew it up and Donald Duck appeared? You rearrange those dots. I mean, that's another possibility. And it turns out that that's exactly what's happening. We start out with Mickey Mouse and we end up with Donald Duck. Because it turns out we're shunting that epistatic variation into main effect. And so if we have an allele that starts out really good, it may end up really bad. And if we have one that's pretty mediocre, it may end up being the best. For those of you who are statisticians, who think about analysis of variance, think about this. You know that when you first learned statistics and you learned how to do your statistical tests, they maybe started out with a perfectly balanced design. And you learned how to calculate the variance components by hand. And you would learn what's called sequential sums of squares, or type 1 sums of squares. And it works, as long as you have a perfectly balanced design. But of course, when we actually go out in the real world, we can't do that. We can't, I have done in my life one perfectly balanced experiment. And so what do you do? Well, what we do is we use type 3 sums of squares, iterative sums of squares. But imagine we were forced to stick with these hand-calculated type 1 sums of squares from the pre-computer days of the 1930s and what have you. Well, what would happen is that if we got an unbalanced design, say we had over-representation of some cells and under-representation of other cells, those interaction terms, if there was a two-way interaction, those interaction terms would start getting shunted into the main effect. And that's exactly what's happening. We're shunting the interaction between the two loci into the main effect. And that, if those are in different directions, there's a pretty good chance that you will change the order of which these alleles will happen. You can actually calculate the probability that two randomly drawn alleles will change their order in a certain percentage of the populations. So anyway, that's what's happening. But the important thing is that if we go through a bottleneck, we get one shift. If we go through a bottleneck in another population, we may get an entirely different shift. So that this allele, which is mediocre, might be very good in one population and very bad in the other. And you can see what that's going to do. If we move from this yellow allele into this population, suddenly you get a really loser being really good. But on the other hand, if this individual moves over here, their offspring are trash. So how are we going to study this? Well, essentially what we're going to do is we're going to take our alleles, and we can either do it as sires or we can do it as alleles. Here, let's imagine that we are using alleles, the A1 and the A2 allele, and we can measure the average effect of that allele in a whole bunch of different genes. And then we can say, then we can actually do our two-way analysis of variance. What is the local average effect? What is the average effect of the I allele across all possible populations? We can calculate what is the effect of the jth population across all possible alleles. And of course it will have an effect. You know, if you have a brown mice and you mate it with a white mouse, they're all going to be lighter. And if you made it with a black mouse, all of its offspring are going to be lighter. There may still be variation, but it will be shifted. And that's what this is about. This is what we care about, the A alpha ij, the interaction between the average effect in that population and the Deem effect. And so this is what we're interested in. This is the two-way interaction. And what we expect is that, let's think about this for a second. If we start out our population, which is completely non-inbred, we take a population and arbitrarily assign our mice to different groups, to different subpopulations, and then we take an allele and we insert it in all of those different populations, they're all the same. And so there won't be any interaction because there's no demic effect. The alleles may be different, but there won't be any Deem effect. As the population inbreeds, as this metapopulation inbreeds, and the subpopulations become more different, those interactions will take place, and this will start becoming greater and greater. And so that is, that's essentially what we can do here. And so we can actually calculate this variance in local average effects. And this shows what it is. Turns out the dominance and additive by additive epistasis go up like that. So it's just simply as a function of, well, first of all, let's look at the additive effect. This is our standard model. That line right there is our standard model that you all learned. When you divide a population, what happens is, yes, it becomes more different. We looked at the populations, it became more different. But what the alleles do doesn't change. So if we take allele 1 and allele 2, we put those two and we look at those two alleles and we move them from population to population, the distance between those two stays constant. Now, as we have additive by dominance, which is a little hard to figure out because there's a dominance locus, the additive locus and a dominance locus. The breeding value is kind of the average of these two, follows this one a little more closely. What we're doing, and additive by additive and dominance by dominance, what we're doing is we're saying as we inbreed, if we measure these two alleles in population 1, we go to population 2, they may be different, and population 3, they may be reversed. And that's what this is measuring. This is measuring how much the populations do different things in different populations. This is a really interesting thing, because it turns out that the increase in additive genetic variance that you get has to come from somewhere. And where it comes from is moving those, is essentially fixing alleles and moving those epistatic interactions start to effectively disappear within populations and reappear among populations in the context of the variance in local average effects or local breeding values. Really very cool. Now this is another really important thing, which I don't think I have on the slide, to realize is that what we've really described is, what I'm really describing here is two kinds of population differentiation. We're already familiar with the differentiation of population means. You know, if you take a bunch of populations and you take a bunch of insects or mice or flies or whatever, put them in different populations and leave them for a long time and measure some phenotype, they become different. You know, they maybe have different coat colors, they may have different behaviors, but they become different from each other. That's differentiation for population means. What I'm talking about here is differentiation for what alleles do. Those two are unrelated to each other. Because one of the big contributors to differentiation of population means is additive effects. Remember, that goes to 2FVA. It goes up, becomes huge. But it has no effect at all at differentiation for population means. Turns out that dominance has essentially, at fixation, has no effect. Pure dominance has no effect on the differentiation of population means. But it has a huge effect on the differentiation of average effects. And so to me, this is one of those things. One of the things that people will say is, how different do two populations have to be before they're species? And if you're talking about differentiation of population means, I would argue that's meaningless. Where it becomes important, the differentiation you need to know about is here. Because this is, you know, if we accept Meyer's definition of species, If we pretend that Meyer's definition of species is correct, then how different they look is no bearing on the process of speciation. What has a bearing on the process of speciation is whether or not you can cross and produce viable offspring. And you can see how that can happen. This is that graph I showed you before, and again, well, it's not quite the same. Yeah, here's the purple allele, very good in one population, very bad in another population. And so we can imagine we take that population, select out the bad ones, and keep the good ones. And notice that in this population, we save the orange, blue, and purple allele. In that one, we save the blue, orange, and green allele. Sorry, this is red, blue, and purple, and that's blue, orange, and green. So a blue allele, in this case, is able to move across, but some of these alleles just simply can't make the transition. Okay, so can we use this in the real world? And this is an exercise I did quite a while ago. This is Domelli in 1995 did a cross between teosinte, which is a progenitor of corn, and maize, which is of course corn. And he did the cross into a teosinte background, identified a bunch of QTLs, and here is the A. There's an A allele and a B allele. Here's their formal description. Teosinte means that these are the A's, that A alleles coming out of the teosinte background. Here's the B alleles coming out of the teosinte background. And this is a heterozygote, this is the maize background. And what we can see then is that this is percent of cupules lacking a spikelet. Don't fool yourself, this is percent of the kernels which look like corn. And it's into a maize background, into a teosinte background. Even at their best, they're pretty pitiful. But what you can see is we can actually fill in these 9 genotypes using a QTL study. And these are the values. And what you can see is that, whatever it is, it's not additive. It turns out this is really cute. And I don't want to do it in this class, but if anybody's interested, I can show you. You can actually take this number, these numbers, you can throw them into your favorite statistical program, and you do a multiple regression using type 1 sums of squares onto those pure variance components. So you basically put those variance components in as dummy variables, and you do a regression of these actual numbers onto those variance components. And when you do that, what happens is you can actually say what percentage of the variance is in that population is additive and what is due to each of those different components. And so if we do that, we come up with this. This is the 40% of the variation. If we have a gene frequency of 0.5 at both loci, 40% of the variance is additive, 20% is dominance, and 40% is collectively epistasis of all those different kinds. And I just lumped those together so you didn't have to see all of them. And so, if we look at the variation within populations, variation in population mean gets huge, but notice the additive genetic variance starts out pretty low and it increases for a while. And so this is a population which is able to respond to selection. Its ability to respond to selection becomes greater as inbreeding occurs. This shows the variation in the average effects of the A and the B loci. And what that's telling you is that, in fact, they start out being effectively, what you end up with is that they do different things in different populations. They do different things in different populations. They're going to have effects which are that change from population to population. This actually turned out to be remarkable, because here is a plot of the local average effects for the maize allele and the teosinte allele. This is the teosinte background. This is the maize background. This is something which is pure maize. This is something which is pure teosinte. At least if those two QTLs. And what we see is that in that pure QTL, in that pure Teosinte background, the A and the B, the two alleles, yeah, this is just one allele, I'm sorry, this is a single allele, a single locus, and this is the maize allele, and this is the Teosinte allele. When we see is back in the Teosinte background, they're neutral. They're neutral, and as we selected for corn, they started having big differences. And to me this was remarkable because one of the things that's very interesting about corn is that corn started out, it just appears in the fossil record. You know, if we look at the record, there's Teosinte, 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 corn. How did they do that? They didn't wait for new mutations. There wasn't enough time for new mutations. That variation was in Teosinte. Well, this gives us a hint. Maybe a lot of that variation was neutral, or nearly neutral, and that when breeders started inbreeding it a little bit, that you started getting differentiation in something you can select on. And that what makes the difference between Teosinte and corn is stuff which was present in Teosinte, but in that well-mixed background had no effect. It's only when they're all assembled together that you actually get corn being corn. So there's a bunch of other fun things we can do with these models. We can add migration. And I did this just for fun because we've all heard the old adage, one migrant every other generation is enough to destroy population variation. Well, actually, no. One migrant every 4 generations maximizes additive genetic variance. This is, what I did was I calculated, used NM to calculate the inbreeding coefficient. And then I said this is the number of migrants per generation. And then this is the additive genetic variance given additive, epistatic, or dominance. You know, so we just said, these are the leading terms. We can think of it as saying, let's imagine that the additive genetic variance is 1. So in a fully mixed population. So with 3 migrants per generation, we're up pretty close to 1 for the additive effects. 3 migrants per generation, the epistatic, dominance, and additive by dominance, etc., are starting to get pretty low. But when migration is very low, we get a huge amount of additive genetic variance conversion taking place. This shows the variance and average effects, and again, at one migrant, of course, it's maximum at no migration, but at 1 migrant every 4 generations, it's pretty high for all of the different terms. So again, I think we can add a new, you know, it's just sort of almost jokingly can add a new term idea that 1 migrant every 4 generation is optimal for speciation to occur. Okay, we can also do exactly the same reasoning for cytonuclear effects. This is the inbreeding coefficient for additive, for cytonuclear. So this is additive by cytonuclear interaction, dominance, and dominance by cytonuclear interaction. This is a variance within genes. Again, we see a conversion of cytonuclear interactions into additive effects. This actually turns out to be pretty interesting because it turns out that when a new mitochondria sweeps into an area, it has the potential to shift what alleles do and change the selection pressure, and then the selection comes along and has to adapt to that. Again, we get the same residual, the same variance in local average effects, and dominance by cytoplasm, and additive by cytoplasm all contribute. Of course, additivity does not. Turns out it goes the other way. We can say this is the cytoplasmic variance, this is the additive by cytoplasmic variance, this is a variance within genes, dominance by cytoplasmic, this is a variance in cytoplasmic effects. One thing that's kind of interesting to notice, we worked on this a little bit. It turns out that with cytoplasmic effects and 2 sexes, cytoplasms are only transmitted by females, and they're haploid. Whereas nuclear is transmitted by both males and females, and it's diploid. So the, I don't know if it's the right term, but the effective population size of cytoplasm is 1/4 that of the epistatic, of the nuclear. And so what that means is that the inbreeding coefficient goes up much faster for the cytoplasmic inbreeding coefficient. And as a consequence, it turns out that most of that cytonuclear interaction gets converted into genetical effects. And so selection, so actually, you can imagine one of the things I've worked on a little bit is Wolbachia. Wolbachia will sweep into a population, it's cytoplasmically inherited. That can then drive, it comes in very rapidly, and that can drive selection on the nuclear genetic effects. And most of that cytoplasmic effect shows up as additive genetic variants in the formal sense. Okay, so this got me thinking. This will be more or less the last topic, and then I'll let you go. What happens if we think about that a little bit, and that X is a transition matrix, and everybody from time immemorial has calculated it as genetic drift. But it can be anything you want. Any transition matrix you want to throw in there. So I said, what the heck? Let's put in genetic drift. Okay, I've already done it. We know how to do that. But we can now put in selection. We can also put in mutation. We can also put recombination in. And it turns out we just simply calculate all those transition matrices and multiply them together, and we get this total transition matrix, which has elements of all of these components in it. And we can do the same process as we've done before, except this is now just the total variation. There's a problem with this. That is, we're combining drift, recombination, selection, linkage, disequilibrium. All of those have to be incorporated into there. And so, I think I have this slide twice. It turns out we can't use the tricks of linear algebra because selection and drift are two different universality classes of models. Universality classes, this was really disappointing to me when I first started working with complex systems. And I'd go to these complex system things and I would say, oh, additive by additive epistasis is really cool. And they'd say, oh, you mean different types can't get along? No. You're reducing it all to the same. You're saying they're all the same. Well, they are all the same model. They're dispersive effects where unlike types don't get along. Selection is different. There you're going to a point. There you have a target you're going to. And so that's a completely different class of models. You can't generically say it's a dispersive model with, with complications. You have to say it's a directional model with complications. So that's one thing, and the other is that the matrix size is huge. So here it is, two universality classes. The standard tricks can't be used with linear algebra. They simply don't work. What you can do, though, is you can still just do forward iterations. And I'm hoping that I can find a good mathematician to help me with looking at regions of these models, which is why it's not published. And then the other problem, of course, comes from the computer world, which is size. There's 2n plus 1 population states for the A1 allele, 2n plus 1 population states for the B1 allele. There's 2n plus 1 population states for the A1, B1 chromosome, many of which are 0. This gives you the population states is 2n plus 1 cubed elements, and it's 2n plus 1 cubed squared, 2n plus 1 to the 5th elements in the transition matrix. And so this gives us, for n equals 16, 1.2 billion elements, and 75 billion when we go up to a population size of 32. What happens is it simply becomes impossible to calculate on your little desktop computer. And basically it becomes an array size problem. So I have been able to get it up to 16. I've never tried to push it beyond that. It goes up really fast after that. But the beauty of this is, finally we can incorporate selection and linkage disequilibrium into the population. And what we discover is we wasted our time. This shows you what happens. This is the additive genetic variance. And there's two lines here. There's a red line and a blue line. It turns out that selection acts on associations. So if you have additive by additive epistasis, the A1B1 gametes chromosomes are better than the A1B2 chromosomes. And so in that case, this is a recombination of 0.5, free recombination. Those are going to be selected preferentially, and that does set up a linkage disequilibrium. And what that means is that the additive genetic variance is actually lowered slightly because you can't, because you get these good associations. And with free recombination and you relax selection, the additive genetic variance will increase that much. Same with the total variance among populations will increase as it goes to linkage equilibrium. So that's kind of a lot of work to show you don't really need to worry about linkage disequilibrium. I have not tried this with a tight linkage yet. But there's something else which is really interesting here. This is a population size of 16 with selection. This is a population size of 16 with no selection. This is just pure drift. This is with selection. Notice that the additive genetic variance in both looks very similar. It goes up a little more with drift than it does with selection, but both of them are going up very quickly. And what you should notice is that this is taking, 40, 50 generations to get up there, whereas this is taking 9 generations to maximize. It turns out that selection is decreasing the effective population size. This is not acting like a population size of 16. It is acting like a much smaller population, maybe 4 or 8 individuals. And so what we see is that selection is decreasing the effective population size. Selection is generating its own additive genetic variance. And so that's a really pretty cool feature. And I knew there was something I left out here. What I meant to put in, and I forgot, is that in fact if we actually do a simulation with this, what we find is that when you have epistatic interactions, a population responds very rapidly to selection. And you can have two populations which both have epistasis, and they will respond very similarly. But what happens is you start getting a breakdown. If you cross between the two populations, you start getting a breakdown of the F1. Speciation occurs. Anyway, if we look at additive by additive epistasis, we can actually plot this. This is a population size of 16, so there's 33 different states, and of course Excel is so nice to us. We have this is 0, this is 32. And so I started out with 16 A alleles, big A alleles, and 16 big B alleles. We're going to assume additive by additive epistasis. And if we do that, this is what happens when we have selection, drift, and linkage. And what we see is that this is exactly the sort of distribution you would expect in a neutral population, except that it seems to be squeezed along one axis. And as we expand that, we eventually get this bar which is moving across this side. And eventually it will go off and we get fixation of the A1, A1B, and the A2B2 alleles with this ridge across here as it goes up into the two sides. And I think, yes, I have it right here. And we can see what's going on. This is, this is the stuff I showed you before. We can actually plot the additive genetic variance. Again, this is the beauty of the Markov chain approach. This is the additive genetic variance for the population at different gene frequencies. And I started right here at that valley where there is no additive genetic variance. The additive genetic variance is going to dive in the corners as we get to fixation. And what we're going to do is we're going to have maxima at the intermediate gene frequencies. This is the fitness surface, and we're starting right here at a saddle point. Now, in an infinite population, we can just stop right there. It's not going anywhere. there's no additive genetic variance. But in a small population, there's going to be genetic drift. And the tiniest amount of genetic drift is going to drive you off of that optimum, and you will then move to one of these, eventually to one of these 2 points. These are our fitness minimum, pits of despair. And so the population is constrained to that slope, to that saddle point. Starting here, it's going to move to the 2 sides. But of course, genetic drift continues to be a process. And so if we go back, we can see that, in fact, here's our fitness saddle, and then here's our 2 peaks. We can do the same thing with dominance by dominance. Here we have overdominance, underdominance, and overdominance. So here we have a pit in the middle, and we have the heterozygotes are all good. This shows you that a gene frequency of 0.5, there's no additive genetic variance. This shows you the fitness areas. This is the additive genetic variance. There's a large space where there's no additive genetic variance at all. The individual loci, when you fix one, are under stabilizing selection. So you're always selecting to here. And here's the fitness surface. Fitness is maximum at the corners, at the edges, and the corners are low fitness points. Again, almost neutral, and then it shoots up to the surface. Additive genetic variance gets really high as we get to the corners. So this is what this is going to look like. Number of B alleles, number of A alleles. Again, same distribution. Now it's behaving perfectly, almost perfectly, as if it's a neutral allele, but you might start seeing some cutouts taking place there. And eventually, it's going to expand here. Again, it's staying away from these low fitness corners. And eventually, we get nice little popads. And this is under stabilizing selection, so these are driving these populations towards these intermediate fixation of one of the alleles. And so when we go to these populations, they can either be segregating for the A locus or the B locus. But it's going to be one or the other as a result of drift. All that's neutral. This space in here is almost perfectly flat because there's no additive genetic variance in there. So it's all neutral drift. And eventually it starts looking like this, and we can see the stabilizing selection. So that's that. And I think I will stop there and let people take a break.